I want to be upfront about something before we get into this. The title framing here, The End of Europe, is the kind of language that gets clicks, and it's also considerably more dramatic than what the actual science currently supports. What's really happening is genuinely serious, genuinely worth understanding, and genuinely contested among the scientists studying it, but it's not a settled countdown to catastrophe, and I think you deserve the real, more complicated version of this story rather than the sensationalized one. The subject here is the Atlantic Meridional Overturning Circulation, AMOC for short, a massive system of ocean currents that includes the Gulf Stream and that plays a direct role in keeping Northern Europe's climate as mild as it currently is. Over the past 2 years, a genuine escalating scientific debate has broken out over whether this system is approaching a tipping point, a threshold beyond which it could shift into a dramatically weaker state, and if so, how soon that might actually happen. Some of the most prominent researchers in the field are now describing this as one of the more urgent climate risks currently being studied. Other equally credentialed researchers are urging caution, arguing the evidence for an imminent collapse remains considerably weaker than recent headlines suggest. Both of those positions are coming from serious scientists working with serious data, and understanding why they disagree is actually the most useful thing this video can walk you through. Before getting into the debate, it's worth understanding what this current system actually is and why it matters as much as it does. The AMOC functions essentially as a massive conveyor belt of water moving through the Atlantic Ocean. Warm, salty water flows northward near the surface, carrying heat up from the tropics toward the North Atlantic, warming the air above it along the way, which is a significant part of why Northern Europe experiences a considerably milder climate than other regions at similar latitudes. London sits at roughly the same latitude as parts of Newfoundland and Labrador, but experiences a dramatically different, far milder climate, largely thanks to this ocean heat transport. As that warm surface water travels north and releases its heat into the atmosphere, it cools and becomes denser. And once it reaches the cold seas around Greenland, Iceland, and Scandinavia, specifically the Labrador, Erminger, and Nordic seas, it becomes dense enough to sink deep beneath the surface in a process oceanographers call deep convection. That cold, dense water then flows back southward at depth, completing the circulation loop, eventually rising back to the surface elsewhere and beginning the cycle again. This entire system depends on a delicate balance between water temperature and salinity, since both factors determine how dense and therefore how readily sinking that northward flowing water actually is. And that balance is precisely what climate change is disrupting through several compounding mechanisms working simultaneously. Rising air temperatures directly warm the ocean surface, making water less dense and less prone to sinking in the first place. Melting ice, particularly the accelerating loss of ice mass from the Greenland ice sheet, adds large volumes of fresh water directly into the North Atlantic. And fresh water is less dense than salty water, further diluting the salinity that the sinking process depends on. Increased precipitation and river runoff into the North Atlantic, itself a consequence of a warming, more moisture-laden atmosphere, adds to that same freshwater dilution effect. All three factors push in the same direction, making the water in the AMOC's critical sinking regions lighter and less inclined to sink, which is the physical mechanism underlying every serious concern about the system weakening, or, in the most severe projected scenarios, shutting down entirely. The AMOC isn't simply expected to weaken in a smooth, linear, predictable way as warming continues. What has scientists specifically concerned is evidence suggesting the system behaves as what's called a tipping element, a component of the climate system capable of shifting relatively abruptly from one stable state into a fundamentally different one once a certain threshold is crossed, rather than gradually degrading in direct proportion to how much warming has occurred. The AMOC is understood to have at least two distinct stable operating states: the strong, deep circulation pattern currently observed, and a considerably weaker, shallower residual circulation pattern that multiple climate models suggest the system could shift into once specific freshwater and temperature thresholds are exceeded. The concerning part of that dynamic is that once the system crosses into that weaker state, it doesn't necessarily require conditions to keep worsening indefinitely to remain there. The weaker circulation pattern can become self-sustaining, meaning even if global temperatures were later brought back under control, the AMOC might not simply snap back to its previous, stronger state on anything resembling a short or medium timescale. Over roughly the past 2 years, several high-profile research papers have specifically argued that this tipping threshold is closer than earlier assessments suggested, and it's worth walking through the actual findings rather than just the headlines they generated. A widely covered 2023 study led by Danish researchers Peter and Susanne Ditleson, analyzing long-term sea surface temperature records as an indirect indicator of AMOC strength, projected that a collapse could plausibly begin anywhere between 2025 and 2095, with the most likely timing centered around the middle of this century. In 2024, a separate research team from Utrecht University in the Netherlands, one of the leading research groups specifically focused on AMOC stability modeling, published a paper introducing a new physics-based early warning indicator and concluded that the AMOC currently appears to be on what they described as a tipping course. The most recent and arguably most attention-grabbing addition to this line of research arrived in August 2025 from a team at the Potsdam Institute for Climate Impact Research led by physical oceanographer Stefan Rahmstorf, a researcher who has studied this specific system for 35 years. Using a set of climate model simulations, the team found that under high-emission warming scenarios, deep convection in the North Atlantic's key sinking regions collapses by mid-century in every simulation run, with the broader AMOC circulation then winding down gradually over the following 50 to 100 years, potentially shutting down entirely sometime after the year 2100. Rahmstorf specifically noted that the standard models used in this kind of research generally don't fully account for the additional freshwater being contributed by accelerating Greenland ice loss, meaning the actual real-world risk could plausibly be even greater than what these particular model simulations directly capture. In comments following the study's publication, Rahmstorf described his own updated personal assessment of collapse risk as having risen from roughly 10% to closer to 25%, and specifically stated that the tipping point beyond which a shutdown becomes effectively inevitable might arrive within the next 10 to 20 years, even though the full physical shutdown itself would likely still take considerably longer to fully play out afterward. That escalating drumbeat of research has had real tangible policy effects. In February 2024, dozens of climate scientists wrote directly to government ministers across Nordic countries, specifically underscoring AMOC collapse risk and urging accelerated emissions action. In November 2025, Iceland's government took the notable step of formally designating the risk of an AMOC shutdown a national security threat, a genuinely unusual classification for an oceanographic phenomenon, but one that reflects how seriously at least some governments are now beginning to treat this specific risk. Here's where the honest, complete version of this story requires giving equal, serious weight to the other side of a genuine, ongoing scientific disagreement, because it exists, it's substantive, and dismissing it would misrepresent where the field actually stands. A study published in Nature Geoscience in 2025 reached a considerably less alarming conclusion than the Ditlevsen, Utrecht, or Potsdam research. That research team built a refined ocean physics-based model, specifically incorporating the relationship between water density and the depth at which the AMOC actually operates, and cross-checked their model against real-world observational data, including measurements from the Rapid Monitoring Array, a network of ocean sensors that has been directly measuring AMOC strength across the Atlantic since 2004. Their conclusion? Even under a very high emission scenario, the AMOC would likely experience what the researchers specifically termed limited weakening, somewhere in the range of 18 to 43% by the year 2100, and the team explicitly stated that a full AMOC collapse during the 21st century was unlikely based on their modeling. Separately, a study published in January 2025 examining long-term air-sea heat flux data across the North Atlantic reported finding no clear evidence that the AMOC has actually slowed down since the mid-20th century, a finding that sits in direct tension with several of the more alarming recent projections and with some interpretations of the Rapid Array's shorter observational record. Neil Fraser, a physical oceanographer at the Scottish Association for Marine Science, has acknowledged the recent run of high-impact papers warning of an approaching tipping point while noting that the field remains genuinely divided. And Jonathan Baker, a researcher at the UK's Met Office Hadley Centre, responding specifically to the Potsdam team's 2025 findings, cautioned that the number of extended, beyond 2100 model simulations available for this kind of analysis remains small, meaning considerably more simulation work is needed before the field can properly quantify how much confidence to place in these specific projections. It's also worth noting that the IPCC's most recent full assessment, published in 2021 and still the most comprehensive, formally vetted synthesis of the field's collective understanding, concluded that the AMOC will very likely weaken over the coming century, but assessed an abrupt collapse before 2100 as unlikely, a formal consensus-based conclusion that several of the more recent individual studies described above are specifically arguing should now be revised upward in urgency, though that broader formal reassessment hasn't yet happened. The next full IPCC assessment report isn't expected until around 2029, meaning the field is, in a real sense, currently operating in a gap between formal consensus updates, with individual research groups actively debating where the evidence actually points in the meantime. It's worth pausing on why this disagreement exists at all, since I think understanding that actually matters more than just picking a side. Different research teams are using meaningfully different methods, some relying primarily on indirect proxy indicators like long-term sea surface temperature patterns, others building physics-based ocean models calibrated against direct rapid array measurements, and others running full climate model simulations, extended well beyond the standard 2100 cutoff most climate projections use. Each of these approaches carries its own specific strengths and specific blind spots, and they don't always agree with each other, which is exactly the kind of situation that shows up regularly in any genuinely active, rapidly evolving area of scientific research, well before a field has accumulated enough converging evidence to settle into a single, broadly accepted consensus view. There's also a structural reason this specific debate has been especially difficult to resolve cleanly. Direct, continuous measurement of the AMOC's actual strength has only existed since 2004, when the rapid array was first deployed, meaning researchers are trying to project multi-decade to century-scale behavior from a directly observed record that's barely 2 decades long, forcing heavy reliance on climate models, and on considerably longer, but inherently less direct proxy indicators like sediment cores and temperature reconstructions to fill in that gap. Reasonable researchers can, and currently do, weigh those different lines of evidence differently, and that's precisely why you're seeing genuinely divergent headline conclusions coming out of equally credentialed research groups over roughly the same 2-year window. Regardless of exactly when or whether a full collapse ultimately occurs, it's worth being specific about what the projected consequences actually are, since this is where the end of Europe framing, while overstated, isn't pulled from nowhere. A significantly weakened or collapsed AMOC is projected to bring meaningfully colder winters, reduced rainfall, and more severe winter storms specifically across northwestern Europe, a genuinely counterintuitive regional cooling effect happening within an overall warming planet, driven by the loss of the ocean heat transport that currently keeps the region considerably milder than its latitude would otherwise suggest. Beyond direct European climate impacts, researchers have identified a range of additional consequences extending well beyond the Atlantic region itself, including substantial additional sea level rise concentrated specifically along the eastern coast of the United States, reduced capacity for the ocean to absorb atmospheric carbon dioxide, sharply reduced oxygen supply reaching the deep ocean, and likely significant ecosystem disruption across North Atlantic marine food webs that currently depend on the nutrient transport the circulation system provides. A 2025 study specifically modeling the collapse scenario projected that if a tipping event does occur, the resulting transition wouldn't happen instantly. Current model simulations suggest it would take more than 100 years to reach a substantially weaker state once the tipping threshold is actually crossed, a genuinely important detail that complicates any narrative implying a sudden, near-term climate shock. That combination, a genuinely severe set of potential consequences, paired with a transition that even the most concerned researchers expect to unfold over many decades rather than overnight, is part of why getting the framing right actually matters here. This isn't a ticking clock counting down to a specific catastrophic date. It's a gradual, still uncertain risk that compounds the longer meaningful emissions reductions are delayed. Exactly the kind of risk that becomes more, not less, manageable the earlier it's taken seriously. Reflecting that gradual but serious risk profile, several researchers directly involved in this field have specifically argued that policy planning shouldn't wait for the scientific debate described above to fully resolve before beginning to prepare. A 2026 paper published in PLOS Climate specifically called for AMOC collapse risk to be integrated directly into national climate adaptation planning, and for the risk to be explicitly factored into international emissions reduction commitments going forward, arguing that by the time early warning indicators can provide a fully reliable signal that a tipping point is imminent, meaningful preventive action may already be too late, precisely because of how slowly and how far in advance the underlying dynamics described above actually need to shift. That's the core argument behind what researchers in this space often refer to as the precautionary principle. Given that the AMOC's early warning signals, by the nature of how the system's physics work, likely can't be detected with full confidence until relatively close to an actual tipping event, and given that the consequences of getting this wrong are severe and difficult to reverse once triggered, several leading researchers argue that the responsible policy response is to treat the risk seriously and act to reduce emissions now, rather than waiting for the kind of ironclad, fully unambiguous scientific certainty that this specific system may simply never provide clearly enough or soon enough to be genuinely useful as an advance warning. It's worth understanding the actual monitoring infrastructure behind this entire debate, since so much of the disagreement between research groups traces back to genuine limitations in how directly this system can currently be observed. The Rapid Array, formally deployed in 2004 and jointly operated by UK and US research institutions, consists of a chain of moored instruments stretched across the Atlantic at roughly 26 degrees north latitude. continuously measuring temperature, salinity, and current velocity at different depths across the entire width of the ocean basin. By combining those measurements, researchers can calculate a real-time estimate of total AMOC transport strength. Essentially, how much water volume is moving through the overturning circulation at that specific latitude, at that specific moment. This was, when it was first deployed, a genuinely significant advance, providing the first continuous direct measurement of the AMOC's actual strength, rather than relying entirely on indirect proxies or infrequent research vessel surveys. But 2 decades of continuous data, while genuinely valuable, is a remarkably short record for detecting a long-term trend against a system that naturally fluctuates considerably on shorter timescales due to weather patterns, seasonal variation, and multi-year ocean oscillations unrelated to any long-term climate-driven weakening. Separating a genuine, sustained decline from ordinary short-term natural variability requires either a much longer direct observational record than currently exists, or reliable indirect proxy methods capable of reconstructing AMOC behavior further back in time. That's precisely why researchers have turned to methods like analyzing long-term sea surface temperature patterns in specific regions of the North Atlantic thought to correlate with AMOC strength, or reconstructing past ocean conditions from sediment cores and other paleoclimate records stretching back centuries or millennia, each of which comes with its own set of assumptions and uncertainties that different research teams reasonably weigh differently, which circles back directly to why the field currently contains such a genuinely wide range of expert conclusions, rather than a single settled answer. Part of why researchers take the AMOC tipping point question as seriously as they do, even amid the genuine uncertainty over exact timing, is that this isn't a purely theoretical, unprecedented scenario dreamed up by modern climate models. Paleoclimate evidence indicates the AMOC, or systems functioning similarly to it, has actually undergone abrupt shifts before deep in Earth's climate history, providing at least some real-world precedent for the kind of rapid, self-sustaining transition modern researchers are specifically worried about. The best documented historical example is an event known as the Younger Dryas, a sudden, sharp return to near glacial conditions across the North Atlantic region that occurred roughly 12,900 years ago, interrupting what had otherwise been a period of steady warming as the planet emerged from the last ice age. Evidence from ice cores and sediment records indicates this abrupt cooling event was closely tied to a major disruption in North Atlantic ocean circulation, widely believed to have been triggered by a massive pulse of fresh meltwater draining into the North Atlantic from a large glacial lake as ice sheets covering North America retreated, diluting ocean salinity in a manner broadly analogous in mechanism, if not necessarily in scale or precise cause, to the freshwater dilution effect currently being driven by accelerating Greenland ice melt. This kind of paleoclimate evidence doesn't tell researchers exactly when a modern AMOC tipping point might occur. The Younger Dryas involved a considerably larger, more sudden freshwater pulse than anything currently occurring in the modern North Atlantic. But it does provide genuine physical confirmation that this specific ocean circulation system is, in principle, capable of shifting abruptly between distinct states once sufficiently disrupted, lending real, historically grounded weight to the theoretical tipping point framework driving current concern, rather than that framework resting purely on untested modern climate model projections alone. I opened by pushing back on the end of Europe framing, and I want to close on the same note because I think it matters. The AMOC is a genuinely important, genuinely at-risk system, studied by serious researchers who have spent entire careers on this specific question. And the honest range of expert opinion currently runs from collapse this century is unlikely to the tipping point could effectively be locked in within the next couple of decades. A real, substantive, unresolved disagreement among people who all have access to the same underlying physics and a considerable amount of overlapping data. That kind of genuine scientific uncertainty doesn't mean the risk isn't real, and it doesn't mean you should tune the story out until scientists eventually agree. It means the appropriate response looks less like blind panic over an inevitable, imminent catastrophe, and more like taking a serious, well-evidenced risk seriously precisely because of how severe and how difficult to reverse the potential consequences are. Exactly the kind of situation where acting on incomplete but genuinely alarming evidence is the more responsible choice, rather than waiting for a level of certainty this particular system may not offer until it's already too late for that certainty to actually be useful. If you take one thing away from this video, I'd want it to be the shape of the disagreement itself rather than a single number or a single date. This isn't a story where credible scientists are split between nothing is happening and everything is happening. Every serious researcher working on this agrees the AMOC is under real physical stress from a warming climate, agrees the underlying mechanism, warming water and freshening salinity, undermining the system's ability to sink and circulate, is sound physics, and agrees the Potential consequences of a serious weakening or collapse would be severe. What's actually being debated is timing and probability, not whether this is a genuine risk at all. Given the stakes involved, that narrower disagreement is still more than reason enough to take this seriously, and considerably more useful to understand than either the reassurance that everything is fine or the headline insisting Europe's end is already scheduled.